Good. So Oxendahl, stochastic differential equation introduction with application is a very introductory level text. It's somewhat too basic for our needs, but it's a very good starting point if you are totally lost. This and this Karadza, Shreve, Brownian motion, stochastic calculus, and Schilling I would consider as essentially main reference for the first part of the course. Both Schilling and Karadza, Shreve build up on some material from Liptzer-Shiryaev statistics of random processes and on the book Stochastic Differential Equation by Gichman and Skorokhod. Unfortunately, the last book exists, as far as I know, only in Russian and maybe in German, but not in English, while being an excellent book. With some nitpicks, but however. For the latter part of the course, we will use Graham Talai's stochastic simulation and Claude and Platen as classical references. Now, Kunita is an advanced text on properties of stochastic differential equation, how they can be combined by starting points. And Proter provides an alternative and, in some sense, more modern approach to constructing stochastic integrals. However, we will not be really using what is in Proter. If you are interested in something related to measurability and related problems, it should be covered by Proter, Karadza, Shreve, and Schilling. Occasionally, I will use other references. I haven't put them in here, especially when we are going to discuss some relation between stochastic differential equation and partial differential equations. But I think it's going to be like 3 or 4 parts from different books, so it doesn't make sense to include them here. Now we can, I hope that answers the question I got. Also, we have a new participant, it seems, Igor, because I cannot recall who you are. Please contact me via email.
Good morning. No, I'm not new. I has already been here and I contacted you.
Oh, okay. Thank you very much. That's my bad. Because people keep coming but never contacted me, and thank you. Then we welcome again. So let's start with recalling what we did last time. So we consider so-called simple progressive processes, which can be which is defined as this: t equals to 0. This part is irrelevant, effectively. It doesn't affect the value of the integral at all. And here alpha k indicator from tk plus 1 for some fixed non-random t, k, t. And here we said that alpha 0, alpha k are bounded random variables, such that for every k, alpha k is f tk measurable. And the corresponding eta integral at time t were defined by us by the sum k from 0 to n minus 1 alpha k wt k plus 1 minimum t minus wt k minimum t. I wrote it last time in a slightly different manner, but it is exactly the same. And then we considered the collection of almost the Hilbert space of progressive phi such that this expression, which is integral from 0 to t mathematical expectation f squared of s ds, is finite. We will denote it L2, and we proved for every f belonging to L2 exists sequence of simple phi n such that phi n converge to f in this norm. And then we said that, moreover, this sequence of stochastic integrals is fundamental in L2 omega, in square mean, just in square mean. And then we defined the integral of our f as L2 limit of these integrals when n goes to infinity for fixed t capital. And for other values of t smaller than t capital, we defined those integrals as indicator 0t f. And the question we were going to answer whether we can define them for all t using this formula simultaneously in a way that the process we obtain as a result has good property, continuous, almost surely, etc. And we established proposition, the last thing we proved last times, that for simple f, we have this maximal inequality. Supremum of the corresponding stochastic integral is just less than this expression, and this is the same in our notation as this object. So now we can finish the construction of our eta integral. For any f belonging to our L2, this mapping on any interval is progressive and continues almost surely. So to do that, consider some fixed sequence of simple that converge to phi, to f in our L2 in this norm. Again, it's almost a Hilbert space, but to make it a Hilbert space, you need to consider classes of equivalence of processes that are modification of each other. And generally speaking, then it's a Hilbert space. If you do not consider classes of equivalence, you need to consider also so-called adapted processes, etc. So this is how it's treated in books, but effectively we're interested only in progressive stuff. And additionally, we can assume that phi n minus phi in this norm squared is less than, say, 2 minus n. So they converge quickly. Then the difference squared n is less than this object, 2 plus 2 phi n minus phi squared, which is less than 2, 1 over 2n plus 1 plus 2, 1, 2n, which give us 2n, 6, 3. And thus, let me introduce such expressions. So mt is supremum over t going from 0 to t. Stochastic integral, the difference of these stochastics two integrals. And in is the event that this difference is greater than 1 over n squared. Then, by the proposition we just recalled, the probability that this happens is less than 4 norms of effectively et phi n minus phi n plus 1 square 2. And so this is less than some constant. Let me write it properly. This equals probability mn greater 1 over n squared, this less than n to the power 4, mathematical expectation of just norm phi n minus phi n plus 1 squared, which is just some constant n to the power 4 and 2 to the power n. So this series is converging, which means by the Borel-Cantema, Borel one, I think, Cantelli-Lima, there exists some number, so for all numbers greater than this number, mn is less than 1 over n squared. The limit inferior holds with probability 1, which means that with probability 1, because this is probability, this event has probability 1, probability 1, such series is converging uniformly on 0t. And why it's important? Because a partial sum of the series is exactly our original integrals. So we see that the limit, this limit exists, it equals to the series, and the series are converging uniformly. The uniform limit of continuous functions, and we know that stochastic integrals are continuous for simple processes, is again a continuous function. So we can take this expression as our stochastic integral. So this limit can be taken and for every t, it equals, if we consider another sequence of simple processes that converge to our stochastic integral, they are going to be equal at time t with probability 1, because they're going to be the same in L2 sense. That means that while this realization of our stochastic process depends on this phi n, on this sequence, for every other sequence, we obtain a process that coincides with this process for every t almost surely, which is exactly the definition of what a modification is of a process. And every stochastic process is defined up to its modification. So we can take any fixed sequence, take this limit, and say this is our process. So we can assume that we always deal with a version of this process. This is almost surely continuous. Important thing to notice that this convergence happens, as we've seen, uniformly on 0t in probability. So now we can establish an analog of corresponding results for just progressive square integrable over the product measure. So firstly, have the very same estimate. Again, as said previously, this for is needed here. And interesting property is we have a process that is already continuous in square mean. Then we can actually construct our stochastic integral as a limit of Riemann sum of special form. So we can't just take any Riemann sum, we need to take Riemann sum where the value of this function is taken in the left end of our interval. And here t and k is just say k t divided over f. So the first follows immediately because we have this for simple processes, and the left-hand side and the right-hand side are going to be converging to the corresponding limits for just progressive square or integrable, because we have also convergence in square mean and uniformly in t, as we have seen from this. From this proof, so how to say it in English? So these supremos are also converging. Let's prove very quickly the second part, which is a useful interpretation. So I will define a special sequence of simple processes. Then this is exactly the stochastic integral of Fn. By definition, what a stochastic integral of simple process. And what we essentially want to consider the difference of these two expressions squared and mathematical expectation. So, but this is just by the isometry, this, and this can be written as the sum over k, mathematical expectation integral over tn k plus 1 f of t of s minus f tn k squared ds, which can be written as tn k plus 1. I can, by the Fibonacci theorem, put expectation inside, as we already did a number of times. And now this is less than supremum over all s r belonging t and k, tn k plus 1 f of r minus f of t and k, mathematical expectation squared. But this for every, so we can write this as tn k plus 1, some function var dr, this function, is this supremum on every interval, and for every r m n of r is going to converge to 0 when n goes to infinity, because this is exactly what effectively continuous and square root means for fixed t, in case they are going to be converging. I will leave the details as an exercise. So this means this goes to 0 by the dominated convergence theorem. And this proves our result. This proposition deals with stochastic integrals with random times. So let tau be a stopping time. I will obviously assume that this is true. Then, if we substitute tau into the expression for the stochastic integral, it is the same as integrating this object on the whole integral, on the whole time interval, or it's effectively the same as integrating this object with square bracket here. So in more familiar notation, this means, this reads T f of s indicator from 0 to tau of s dws, etc. So we can take such expressions and just use them to consider a value of this process, because this is a process in t, and we can substitute the random variable as the time parameter. And because this is a continuous and well-defined object, this is again a good object, a random variable essentially. Let us prove this only in one particular case, when f is simple and tau admits only finite number of values. Why? Because we know that every stopping time can be approximated from above by a sequence of discrete stopping times, and we know that every integrable in the iter sense function can be approximated with simple functions. So if we prove this for this case, we can pass to the limit in proper senses. So I will assume that tau takes value in this set, and I will also assume that these are support points for our t, because if not, we just can add them in this decomposition. Fk indicator from tk plus 1. So if they are not original here, we just add them here, and fk and fk plus 1 might be equal for some special k. Now let's recall something about filtrations. This is tau less than t. Less than t means that it lives here, and this is measurable. So this process indicator tau greater than tau. T greater than tau is progressive. And the difference in L2 sense between tau great, let me write it in this case. Dt. Here should be, wait, this should be this direction, which tau less than t. Now this works. This is, yeah. This is effectively mathematical expectation for 0 to t, indicator that tau just equals t. Dt, and this is 0. So this means then the original statement we can use either the full interval or just the interval without the right side. And now we can consider this new gt, which is f of t, indicator from 0 to tau of t. I'm doing this because this is slightly more convenient to work with. 0 to n minus 1t, fk, indicator that t is greater than, tau is greater than t. This is exactly it. And here we have indicator from tk plus 1, t. Now, tau admits only discrete number values. If tau is greater than t, and t is already greater than tk, this effectively means that simply tau is greater than tk plus 1, since it's already greater than tk. And t cannot be higher than this, can be larger than this. Indicator tk plus 1 of t. And this is f tk measurable. Why? Because we already seen something like this. And that means that G is again a simple process, which means that this object is well defined. We can just write what it is. This is sum from over k, fk, indicator tau greater than t, k plus 1, w, tk plus 1, minimum t minus w, tk minimum t, and that's all. But tau greater than t, k plus 1. If tau is greater than this, that means that this minimum can be written as this. Adding this doesn't breaks anything. They are already greater than. And on the set of those omegas that tau say equal t g, we then have et of g, et. Now, why? Because this disappears, this part disappears when tau less than tk, and here I just take the sum over those k, that this is not zero. But this can be rewritten as now tau equals tg here. Tau equals tg. I can write this as t minimum tg of f. This is our new t here and new t here. This is just a definition of the stochastic integral with respect for f calculated at this time, which is effectively t minimums, which says that et of g is e t minimum tau of f, almost surely. And then passing to the limit, we can obtain what we want. The only problem I think here is that here I should have put tau minimum t, as we can see. Oh, we don't need it here. We don't need it here because tau is less than tau. Corollary in the same notation as is the original statement, we can obtain this stronger result. So now tau just leaves from 0 to t capital, but we still can define such processes because this is essentially what we proved. Sometimes it's useful to be able to write an integral with respect to a random time. This proposition I'm not going to prove because it's very expected and can be proved very similarly as the propositions discuss L2 properties of stochastic integrals with non-random upper limits. So if we have two stopping times, then for any integrable, we have essentially we have the same good properties in L1 and L2 senses as for integrals with non-random upper limits. But now we can consider this special sigma algebra that we defined in some of the previous lectures. And because our Wiener process possesses a strong Markov property with the original filtration, you can do stuff like this. Tau 1 plus squared. And this is mathematical expectation from tau 1 to tau 2, f squared of s ds. So this is analogous to isometry. Again, this is a very expected things because all this happens in L2 sense, and we already know that all that happens in L2 sense is essentially related to the strong Markov property. The strong Markov property we formulated exactly in the way that it is written with respect to this sigma algebra. So everything should be okay. Now, what about calculating stochastic integrals? Overall, this is a problem, and you cannot really expect much success. However, sometimes we know the result. For instance, this W of S dWs, we already calculated on a number of times. Why? Because we just proved this proposition. Then if the stochastic process that is being integrated is good enough in L2 sense, you can obtain the stochastic integral as the limit of the Riemann sums. But we already considered such Riemann sums when we were calculating square variation of a Wiener process, and we already know that this is 1 over 2Wt minus T. And another example that I will give is just if f is deterministic continuous, then the process is a centered Gaussian. Why? Because for the approximations that we just discussed, we have a sum of Gaussian independent random variables, because increments of a Brownian motion are independent over non-interlapping intervals. So the limit must also be Gaussian process. Any limit of Gaussian random variables is again a Gaussian random process. We will see some other examples, but in the setting of stochastic differential equation. Now, I want to talk about multidimensional versions. So up to this moment, we considered essentially only one-dimensional processes, but not much. What we did was related to the processes being one-dimensional. So when consider W1, WD is a Brownian motion in RD, that is, every single coordinate is a Brownian motion, and all coordinates are jointly independent. Ft T is its augmented right continuous filtration of the whole process. And then we can consider, say, Fig, where I ranges from 1 to n, G ranges from 1 to D, such that everyone is L2. Then we can define eta I of t as, and starting from this moment, we will actually use this notation more and more up to the moment where we totally switch to this maybe more familiar to you notation for stochastic integrals. So this is just a sum of stochastic integrals. And then we can define eta as a process that has this eta i's as its coordinates. So what we obtain here is effectively a multidimensional process that is represented with stochastic integrals, and everything that we set for one-dimensional case can be translated here, and in particular, mathematical expectation of the norm eta of t squared, this norm is calculated as Rn, can be written as a mathematical expectation of the integral from 0 to t phi of t squared, and this is Hilbert-Schmidt norm, so it's just the sum of so this is the analog of this norm squared in this case. This is the Hilbert-Schmidt norm is just the sum of squares of all coordinates of the matrix. I will not care much about the multidimensional Ito calculus for a moment. Later we will use it regularly, but as for now, the main conclusion is that you can do this stuff. You need the filtration with respect to the whole process, or with respect to the all coordinates simultaneously. And then you can integrate with respect to every coordinate, combine them into linear manner and produce such multidimensional processes. Now, definition. If a process psi of t, t from 0 to t, is such that psi of t can be written as some constant and sum of two integrals, et of sigma, for some a and sigma, such that mathematical expectation and starting from this moment, we will actually assume that everything we deal with is progressive. So I will not repeat that A and sigma should be progressive. We will not consider anything except progressive process. Even though the whole Iter calculus can be developed for more general class of processes, we already discussed it a bit, which are adapted processes. But every adapted process has a modification that is progressive. So we are not losing much by restricting our attention to this case. So if this holds, psi is called an Iter process. And notation which we will adopt is that this can be written as d psi of t equals a of t dt plus sigma of t dwt. This is a notation in the terms of stochastic differentials. This is stochastic differential. And if you really want to add, specify starting point, you will add this. But sometimes you don't even care about the starting point. Remark, an important remark, that the condition is too strong, but I will take it because we are discussing everything in terms of L2, in terms of L2. And effectively what we need here for all this, what follows to work is that this is well defined and sigma is square integrable on 0 of t almost surely. And this is just the Lebesgue integral, so we just need a to be in L1, effectively almost surely, but this is a more general case and I will not consider this. So now we are ready to formulate a central result of the whole theory, which is the Ito formula, or sometimes called Ito lemma. It's still a theorem. So let psi be an Ito process of this form, a of t dt plus sigma of t dwt. Then for any function that is one time continuously differentiable with respect to t and two times continuously differentiable with respect to space variable, I'm sorry, the process f t psi of t is again the Ito process and admits the following representation: plus integral from 0 to t d over dt f, s, psi of s ds plus integral from 0 to t d over dx f s psi of s Now, this should be understood that d over dx f of s and x at point x equal psi of c. But we will write this in this form. A of s ds plus integral from 0 to t d over dx f s psi of s sigma of s dws plus 1/2 integral from 0 to t. This is where the second derivative with respect to space appears. Sigma squared of s ds. So in terms of stochastic differentials, it's typically written in this. This is d over d t f t psi of t plus d dx dt plus the derivative with respect to space. Effectively, d psi of t, this is sum of two integrals, a dt plus sigma dwt, and plus a correction term. 1/2 d squared dx squared ft psi of t sigma squared of t dt. Again, I will repeat, this is the central part of the whole theory. Also, this result is not directly related to everything having second moment, so it actually works for, as I said, for more general eta processes. However, I will prove it only in this setting of L2 theory. I will formulate also a multi-dimensional version, multi-dimensional version, but we will prove only one-dimensional version. The proof is very similar in multidimensional case. There will appear some cross terms that will cancel each other, but whatever. So we have the process psi with n coordinates such that for every coordinate we have this decomposition. J from 1 to d, sigma j k of t dw k of t. And for any f that twice continuously differentiable in this sense, we have this expression for its stochastic differential. Again, I recall that this is a formal way to write something that happens in the world of integrals. So effectively, the stochastic integral is just a shortened version of this form. But because it's redundant to write those integrals every single time, people and we will always almost exclusively use this shortened version. So this is d over dt plus integral. Now let's us be careful. D over dx k f t psi of t a of k of t dt plus sum k from 1 to n d over dx k f t psi of t. And here we have our stochastic part, just in this form. P of t, dw, g of t, and correction with 1/2, which is 1/2, again, sum from k to 1 to n, d dx k squared, f t psi of t, sum j from 1 to d sigma. It's not correct. It's not correct. Sorry. It's not correct, obviously. I need all derivatives. K1, K2 for 1 to n d squared dx K1 dx K2 ft psi of t. And here we have, I think, just this d sigma squared K1 of sigma g t sigma K2 of g of t dt. Yeah, it looks good. So this is a multidimensional version. All derivatives up to the second order in space and only to first order in time. I will need two additional lemmas. So first lemma, now we are back to one-dimensional case. First lemma is useful in many cases, not only this. And it says that if we have convergence of coefficients for our stochastic difference is L2, and we have the corresponding Ito processes, so this is an of t dt plus sigma n of t dwt, and this is the psi of t is a of t dt plus sigma of t dwt. Then we have this form of convergence and probability uniformly over t, psi of t minus psi n of t goes to 0 and goes to infinity. So if our coefficients of in our stochastic differentials are L2 convergent, in this L2 Gaussian sense, everything is going to be convergent in probability and uniformly in t. And effectively, the proof is just one-liner because we have this estimate psi of t, psi n of t, greater than epsilon is less than 1 over epsilon squared, where I used just a very simple inequality for squares. And the fact that the supremum for t of such expression for stochastic integrals is dominated by 4 such norms. And this goes to 0, goes to infinity. This is a very fast proposition we considered in this lecture. For simple processes that we just very quickly developed, it's analog for general progressive. Now, the second proposition is the core of the whole proof. This is lemma 2. So I will assume I have two Ito processes. So every time I write this expression, I assume that this are progressive and square integrable in the proper sense. I will not just repeat all those words. And we have b of t dt plus, say, phi of t dwt. I will assume that they start from the same point. We don't need this at all. And b and phi are simple in the second case. And I assume that we have a sequence of partitions Tn0 less than Tnn equal to T capital is a sequence of partitions of interval 0 T capital such that two properties hold. First, all pi n for n greater than some fixed n0 contain all support points for b and phi. And secondly, obviously what we want from our partitions, we want that the diameter of our partition go to 0 and go to infinity. If the first one doesn't hold, you can augment partitions, but it's easier to just assume it immediately. Now, for any f which lives here, that is bounded with bounded derivatives. So derivatives are also bounded. We have such nice convergence. Psi Tnk multiplied by Tn k plus 1 minus eta Tnk. Eta is a simple process. This converge in probability when n goes to infinity to the sum of the following two integrals. Say t dt plus integral from 0 to t f psi of t. Oh, sorry. Here should be of t, sigma of t, dw of t. And this is actually an easy part. This is 1, this is 2. Phi of theta nk, I will explain what is this in a moment. Tn k plus 1 minus eta Tn k squared is converging in probability when n goes to infinity integral from 0 to t f psi of t phi squared, this is phi squared of t dt, where theta nk is a linear combination of values of psi at two endpoints of this interval of our partition for some alpha nk such that this expression is measurable. So we do not assume that alpha and k is a random variable. We do not assume that alpha and k are measurable for all k or for any k. We just assume that the whole expression that happens here is observed here is a random variable, and the theta and k is a combination of these two values. Then it looks very convincing to assume that this holds. In what we will, in the situation where we will use this proposition, this alpha and k are going to be measurable, but this is a trivial result that we will not prove. So this is the reason why we went for avoiding discussion of measurability of this theta and k. So let's start from the following. Let's consider two mappings. The first take t to f psi of t, b of t, and the second takes f psi of t to phi of t, are bounded bounded for independently of omega. Why? Because f is bounded, and these are simple processes, and coefficients for simple processes are bounded also. And piecewise L2 continues, because they are simple processes. Simple processes are just constant on intervals. Thus, the sum n minus 1 f psi t and k delta eta t and k. I will use this notation repeatedly in different contexts, where delta means that we calculate this difference. So if delta f t and k, this means that f t and k plus 1 minus f t and k was just eta here, sum over k for all k's, psi t and k. Here we have b t and k, delta t and k. Why? Because our partitions contain all values of our support points for our original simple b and phi, and this is phi t and k, delta w t and k, because say at eta of t we assume that this is a sum of simple processes. So this is t and k plus 1 of t plus the corresponding sum of the same form with sigma. Now, everything is bounded, so this is going to converge. First part, first term, just ordinary dominated convergence, almost surely. And second term is lemma 1, because it's piecewise continuous. So on every interval where eta is continuous, or more precisely constant, we use this lemma separately. So this is going to converge f psi of t, a of t dt plus integral from 0 to t, f psi of t, sigma of t dw of t. So this proves the first part of the statement. Now the second, step 2. This is the main problem, essentially. So we have this phi c and k, f of theta and k, delta eta t and k squared, and I will write it as a sum of 3 terms. Eventually, but so this is the sum of, let me write it one more time. Eta is b t and k delta t and k plus phi t and k delta w t and k. So by taking squares of the sum, I obtain b squared t n k delta t n k squared plus sum k from 0 to n minus 1 f of theta n k phi squared t n k delta w t n k squared plus a cross term, or more precisely, two sums f theta n k b t n k phi t n k delta t n k delta w t n k. So this is going to be I1, this is going to be I2, this is going to be I3. And we discuss these integrals separately. So let's say step 2.1, I1. I1 is this integral, f of theta n k b squared delta t n k. I1 is less than sum t n k. I will write this one more time just to show calculations. This is just by definition what I1 is. This is less than, I will denote supremum over all real line for any function g of its modulus by g infinity. Or effectively this is the norm g in L infinity R, but I will not bother with this L infinity. I will just put infinity here. So L is less than, phi is bounded, F is bounded, I'm sorry, B is bounded, and the sum has just sum over all k delta t n k squared. But we already did that a number of times. These expressions like sum k from 0 n minus 1 delta t n k, this is just t capital. And here exactly the diameter of our partition. This goes to 0 almost surely. So we can get rid of the first integral. It goes to 0. Now let's consider this cross term, I3. So this is phi f times b times phi delta tnk delta w tnk, I3. So for I3, we have the following. Proceeding exactly as the previous part, we have b infinity, pi infinity, sum over k delta t and k. This is positive by definition. And this is, again, we have supremum over g delta w t and g modulus. This is exactly t. These are just constants, and this goes to 0. Why? Because w is uniformly continuous on 0t, almost surely. It's a continuous function on a compact. It's uniformly continuous. Such supremum must go to 0, again, almost surely. Now we can return to I2. I2 is the sum f of theta and k, phi squared, and delta w t and k squared. So we already assume that this should behave like delta t and k, but in the first power. So this should converge to the integral of I of f times phi squared dt. It's just we need to give enough reasoning why it's happening. So I will consider the difference of I2 phi squared t and k delta w t and k squared minus a Riemann sum that approximates the integral we want to obtain. These Riemann sums are going to be convergent almost surely to the integral we want. And we want to show that this is going to 0 in probability. We want here we will again do some decomposition. So this equals sum over all k f theta t n k delta w t n k squared minus delta w t n k plus, we didn't use this part, so this is going f of theta n k phi squared, I forget phi squared here, t n k, phi squared t n k delta w t n k squared minus sum f theta t n k phi squared t n k delta w t n k squared. So this term then cancels with this term, and we obtain the original expression. This part is this part, and this part is this part. So it's indeed a proper decomposition. I will denote this first one. This and this sum is 2, 2. So for this is simpler. I think we have sum over k pi squared t and k f of theta and k minus f of psi t and k delta w t and k squared. The absolute value is less than pi squared to infinity maximum over j from 0 to n minus 1 f theta n k n g minus f psi t n g. And here we have sum over k delta w t n k just squared. So mathematical expectation, the square of this expression is less than to the power effectively 4. Mathematical expectation of the sum w t n k squared by the Cauchy inequality and times mathematical expectation maximum from g over g from 0 to n minus 1 of these differences, psi t and j squared, and again 1/2. Now, this is constant. This goes to 0 by the Lebesgue dominated convergence theorem. Because everything is bounded and f is continuous and theta and g are built in such a way that they go to psi t and g when n goes to infinity. Let us recall that theta and g is alpha and g psi t and g plus 1 minus alpha and g psi t n j plus 1 for some alpha and g, and I might have forgotten to write this to specify that alpha and g belongs to this interval. So this goes to 0. Now this expression is bounded, again, why? Because it converges to the square of the two variation. I will leave this an exercise and to prove that this is finite. Thus, this part of the integral converges to 0 in L2. Thus, this means that this part of the integrals converge to zeros in probability. In probability, which we wanted to prove. So we are only left with last part of this integral, T1. Here we have mathematical expectation. Let's see what we didn't consider. This part. Half of psi t and k, phi squared t and k, this difference. So we have mathematical expectation. I will rather immediately consider if square mean, because this is how it works. Here we have delta t and k squared minus delta d and k squared. No, squared. Here we have another square. It was a whole sum. We considered such calculations a number of times when we were discussing two variation of a Wiener process. So I will just allow myself to write it in a simpler way. This is mathematical expectation of just a sum of psi t and k, phi squared t and k. Let's recall that this is f t and k measurable. And this is independent of t and k. So effectively, every time we calculate something for this term, we can get rid of this by putting it outside of the internal conditional expectation with respect to this sigma algebra, and using the fact that this is just delta w t and k squared minus delta t and k squared again with respect to the sigma algebra t and k. Cross term will disappear because the mathematical expectation of this expression is just 0. So for cross terms, we will be considering products of such differences for different k, and because exactly the same reasoning we used earlier, they're going to be 0. So cross term disappear. You can always take additional conditional expectation with respect to this small, to the higher k, delta w tnk minus w squared minus dw tnk mathematical times delta w tn j squared d delta n g, when k is greater than j, f psi tnk phi squared tnk. I am not writing j because I'm taking additional conditional expectation with respect to t and k. Then we can get this out and this out to obtain f psi tnk phi squared tnk mathematical expectation. And this is also measurable with respect to t and k because j is strictly less than j k, delta w squared t and j minus d delta n j mathematical expectation dw tnk squared minus dw delta tnk with respect to the sigma algebra. But this is just zero because this expression is independent of the sigma algebra, so we just need to calculate this mathematical expectation. This mathematical expectation is exactly zero. So there is no cross terms here. And we obtain this expression. And exactly as in the proof for the two variation or stochastic of a Wiener process, you can prove that this sum converges to zero. Because you can get rid phi, you can get rid sigma, and you are left essentially with w t and k minus delta t and k squared t and k. This converges to zero and goes to infinity. This finishes the proof of this lemma. And this lemma, so we have two processes. The second one is composed of integrals of simple processes, and then these sums converge in proper senses. So this is a crucial and main problem in the proof of the Ito formula. So next time we will finish the proof quite easily, and we will start working with stochastic differential equations. In particular, we will see how one can use Ito formula to say something about solution to stochastic differential equations. Please, any questions? Again, if there are new participants, please contact me via email because I need your addresses. I think I see at least one participant who didn't contact me, though I asked. So please do this.
Okay.
Okay, so if there are no questions, I will see you again, and I will repeat. If you didn't contact me this time. Good luck, everyone.
Yeah, thank you. Bye bye.
Bye-bye.
Thank you.
Goodbye.
Thanks.
Goodbye.
Bye.